Hello, good evening, everyone. Am I audible? Am I audible?
Yes, sir.
Yeah, okay, thank you. And is my screen is also visible?
Yes, sir.
Okay, thank you. So let's just wait for 5 more minutes. After that, we will start. So, okay. So, good evening, everyone. I welcome you all to NPTEL live session for Aspen Plus Simulation Software. So, today we are in week 2 class. So, as you all know, every week we have a live session. So in this session, we'll discuss about the previous week course content, like about summary, and we also do some assignment question from previous years. So the motive of this class is to show you how to solve the assignments and like to show you the like real time working with the Aspen software and to clear some doubts if you have regarding the assignment questions. Okay, so this meeting is being recorded, and after the meeting NPTEL team will share the meeting recording and this PPT with you, so you can refer to this. Am I audible?
Yes, sir, audible.
Yeah, okay.
Yes, sir.
Yeah. So if you face any issue in between, please let me know. Okay. So all of you, were you present in last class also, or today is your first class?
So this is my first class. I missed the last week
Okay,
sessions.
okay, okay. So the course instructor for this course is Professor Prabirkar Kumar Shah from IIT Guwahati, and I am his TA Amit Kumar Sharma. So I will be here every Sunday from 7 to 9. Okay. So let's start with the today's class. So today we will cover about, first we will cover in first in first 30 to 40 minutes we will cover the last week summary. Okay, the course content. After that we will do some sample assignment questions. So those questions will be very helpful to you in your current assignments. Okay, and please don't discuss the current assignment questions. Okay, because these classes are meant to like for query for previous assignment, previous year assignments. So please don't ask any question regarding your current assignments, because you should do them yourself. Okay, let's start with the today's class. So is my pointer is visible?
Yes, sir.
Okay. So in Aspen, like in basic process modeling, we have some unit operation blocks. Okay. So these blocks are like already defined in the Aspen. So we can directly use these blocks to do multiple things. Okay. Like if you want to separate something, if you want to do distillation, and if you want to do like some kind of other like splitting the streams and like that. Okay. If you want to apply the heat exchanger and all. So Aspen have already predefined blocks. So those blocks are already predefined. In the background, they have all mass and energy balance equation. So we just need to introduce the block into the flow sheet, and we have to specify the inputs and some like important parameters. So after that, in the background, the mass and energy balance will be done, and you will get the answer. And you can connect multiple blocks in a single flow sheet. So in that way, you can design your complete process. So in this we will cover like these operation blocks, then introduction to unit operations, what kind of operation they do, then unit operations in Aspen Plus. So these blocks like mixer, splitter, separator, exchangers, columns, reactor, and pressure changers. Okay. So basically the exchangers will do the heat balance, the energy balance. Okay. The reactors in the reaction kinetics is important. For the momentum balance will be done in the mixer, splitter, and pressure changers, and the mass balance will be in the separator and the column. So these are the governing equation, you can say. These are very important equation that will be in these blocks. So this is the picture in which you can see the blocks here. Just let me take you to the actual Aspen. So let me share my Aspen screen. Okay. Is Aspen is visible to you?
Yes, sir.
Okay, okay, thank you. So this is the like when you open the Aspen Plus. So I'm using version 12. So this is the window. So last time actually I was not able to access the Aspen, but now I'm able to do it. So let me first start with the this help section. Actually, it's very important. So you can see in the corner, rightmost top corner, there is option for help. You can click on it. If you click on it, then you can see there will be complete help section. So basically it's a manual. So it's the manual for the complete software. So in this manual, you can find your like you can find any help regarding your any query. And like you can also use this manual to understand like to understand the more about the property methods, more about the simulation environment, more about the blocks and all. So there is one option here. So you can type anything here. So it will search that method. So like suppose let me say the what is the meaning of NRTL. So type NRTL. Just press enter. So it will search and it will show the results. So these are the results. So you can click on the results and you can find the required information. Okay. So now here you can see the using the property environment. So click on it. So you can see what about the all available about the property environment. So how to specify component, physical property methods and all. Now let's go to the simulation environment. So here you can see about the defining the flow sheet, how to define it, then specifying the stream, how to specify the stream, like what are the options available, what do you need to specify, then the unit operation models. So you can click on it. So here you can see the overview. So like the unit operation models are used to represent actual pieces of equipment such as distillation columns and heat exchangers like that. Okay, you choose unit operation models for flow sheet blocks when you define your simulation flow sheet. So you have a process in your mind, then as per that you select the particular operation model, the unit operation models, and you connect them as per your requirement. So how to select it, then click on it. So you see, so we have mixer, splitter, separators, and mixer is also like three types: mixer, F split, S split. So mixer like directly stream mixer, and the F split will be stream splitter, and S split will be substream splitter. So there will be more option in S split. Then separators. So we have different kind of separators also. So heat exchange. So you can get like uh, so much information about all these things. So it's like a manual. Okay. So just click on like mixer. So you will get further information. Further, you will click on it, then you will get more information. Okay. So this is the help you can use. So let's go to like a new file. Okay. So here we can specify the components. Just specify like air and water. Okay. You can specify any component here. Just type, if you know the exact name, you can type it. Otherwise, you can click on the find button. You can find it here. Okay. So you can find with like molecular weight. You can find with boiling point. Okay. So you can do your find here. After that, just click next. So then it will come to the next input, required input. So now you have to select the property method. So this the property method, you can also use the method assistant. Okay. So if you click on it, then it will ask you some basic questions. Like if you are not sure which property you should use, then you can use this property method assistant. So like specify the component type or process type. If you know about the component, then you can select this option. Otherwise, this option. Suppose I know the components, you can select on this option. So suppose my component is like hydrocarbon system. So does this mixture contain petroleum, acids, and pseudo components? So suppose no, then you can select further. Like these are the like best options you can use, like Peng Robinson and all. So if you click on it further, then it will show you all the detail regarding it. So if you are not sure about the exact property, you can use this method assistant. So just select your NRTL. Okay, then next. So now your property specification is complete. Now go to the simulation window. So here you can see the model palette. So see here. So at the bottom you can see the mixer F split. There is a model pellets. So here you can see one is mixer splitter. Then there is about separator. So you have different options. Then exchangers. Again you have different options. Then columns, reactors. So in today's class we will cover this mixer splitter, separator, and exchangers and columns. Okay. So in mixers you can like click on it, just drag it here. It will come here. Okay. Then you can connect with the metal stream and all. So you can see there are red option like red arrows and blue arrows. So red arrows are like you have to like you have to connect here a stream. It's mandatory, but blue arrow is optional. Okay, so you need to connect at least two stream in the splitter. One will be the input and one will be the output. Without specifying both these streams, it will not run. Okay, so the red is the mandatory input required. The blue is optional. And if you take your arrow on this like on this arrow, then you will see its feed required one or more with mixing metal stream. And if you take it here, it will show the product. So this will be your like feed or input, it will be your output. And if you click on this one, like if you go to this one, don't click it, so it will be water decant for free water or dirty water if mixing metal stream. So you can separate some water decant here. So this is the basic model palette. Let's go back again to our PPT. So you see here, so these are the model palettes. We can use the model that we require. We can select multiple options and we will go through some examples also. So first in the week 2 we covered mixer S split, F split. So the mixer is mixes more than one stream and lets out one or two outlet streams. Okay. So if the two outlet streams are there, then the second one is the decant stream based on density. So suppose you are mixing, then if there are two outlet stream, then the second stream, that is like the blue one I showed you, that will be the decant stream. Okay, and the heavier liquid will go into the decant stream. It will be depend on the density. In the S split, splits the flow based on the only two outlet parameters, while split fraction and flow. So you need to define the split fraction or flow. These are the parameters. Only two parameters are there. So in S split, we can use only these two parameters. But in F split, splits the flow based on various other outlet parameters, in addition to split fraction and flow, such as limit flow, cumulative flow. So in this F split, we can also do the limit flow, cumulative flow like that. But in S split, we will only do the split fraction and flow. So this is the like example in mixer, two streams are coming. So we are joining this stream into a single stream. So this is the mixer, and again the single stream is there, and we are bifurcating into two streams. So it's a splitter. So this example was discussed in the class in which water, benzene, toluene, like they are coming in a mixer. Now they are mixed. So there is a mixed stream, then there is a decant stream, and this mixed stream is further going to the splitter, and it was splitting into supply line 1, 2, and then storage. Okay, so let's go to the Aspen. Let me show you this example.
Hello, sir. I had a small doubt, sir.
Yeah, please.
Actually, my Aspen is not working, but my Aspen HYSYS is working. So, shall I work out the same in Aspen HYSYS, sir? Aspen Plus is not working, but HYSYS is working.
But Aspen actually these are the regarding the Aspen Plus only.
I know,
So
sir, but the Aspen software is not opening. So what shall we do, sir?
maybe
Shall I
you should,
reinstall?
yeah, either you should like
Because last week I had given the same with the screenshot. I have given it to the NPTEL. Still, no reply has come. So that's why. What should I do?
okay, so maybe you can try to reinstall it, or
Uh,
either like just again
okay,
share the details with the NPTEL team.
so I have shared the same. They had given one Google form where if you have any problem, you'll share the same. So I have shared, but there's no still till date. There's no response from the NPTEL team.
Just put one more reminder actually, yeah, it will be better.
Okay, okay, okay.
Okay,
Thanks.
okay, thank you. So this is the example that was discussed in the class. Okay, so this is the flow sheet. In this, we are using this mixer and then this as a split. Okay. So if you click on like this stream, then it will take you to the details. Okay. Like what is the input variables like state variable like temperature, pressure. Okay. So here you can see. So this is temperature pressure. So 80 degree 1 bar. So it was given in the problem actually 80 degree. Okay. The temperature consider like 1 bar like that. So you can here you can see the total flow rate. So you can define the flow rate here. So be careful with the like basis of the flow rate. Like if you are having mass flow rate, so there is option for mass flow rate, mole flow rate. Okay, so you can change the flow rate option like mole flow rate, mass flow rate. Okay, so if you are defining the flow rate here, then you need to define the value here like mole flow it should be water it should be like 1. Okay, or either you can define the flow directly here also. So then if you press the next button, so actually input was already given, then again go to the main flow sheet, then click on this benzene stream. So for the benzene, you can see the value is 70 degree temperature and the mass of our benzene we have given already. So regarding the toluene, so we have given all the inputs that we have given in the questions. Okay, so we have 3 streams. So we connected 3 streams to the mixture. Uh, we give the inputs, then go to this block mixer. So here you can see it will be vapor liquid. Okay, so it will depend on, you can also select like vapor liquid liquid, but it's only a mixer, so you don't need to do any changes in that when you do the inputs. Okay, then there is this S splitter. So here you can see uh, so we have like 3 supply lines. Okay, 2 supply lines and 1 storage. You can see here, so supply 1, supply 2 and storage. So if you go to this, then there are option specification for each stream. So for supply 1, you can specify like the split fraction. So you have a mixed stream. So from that mixed stream, what should be the split fraction in the supply line 1? So you have mentioned 0.25. So the 0.25 fraction will go to the supply 1. Then you have supply 2, it will be 0.2. Then you have storage. So if you have already defined the 2 options, like supply 1 you have already defined, supply 2 have already defined, then the remaining portion will go to the storage. Okay. Here you can also change the flow rate. So either you can define by the split fraction or you can define by the flow. These two options you have in this S split. Okay. So if you run this model, then you can see the results here. The result summary stream. So we have like benzene, then storage, then supply 1, supply 2. So here you can check all the results, like you can check the mole flows. Okay. You can check the mole fractions. So these are the options you should explore. Okay. So let's go back to the PPT. So now regarding the separators, we have plus
Sir, I
decanter.
have a doubt.
Yeah, please.
Sir, the supply fraction will be given to us, or just we have to assume like we can keep any value?
Actually, it depend on your like what kind of problem you have. Actually, in this system, like
Okay.
they didn't mention it. Like they only
Huh.
mentioned the input stream, so you can decide as you want. But if
Okay.
you are having a real problem, then you will
Hmm.
know that I need like in storage, I need this like this fraction in the storage, okay, and this kind of flow in the storage, and like I
Hmm.
have two supply lines, and these supply lines are further connected to some process, okay.
Okay.
Like
Okay.
supply one is connected to a different system, this one is connected to a different system. So suppose this supply one require at least like you can say 30% of flow, so you can mention that actually, or you can say the 30% composition of this mixed stream, so you can define that.
Okay.
Yeah, so it
It
will depend
it
on your
totally
problem
depends
actually.
on the requirement.
Yeah,
We can say. Okay. Okay.
yeah. So you need to change the parameters as per your requirement. You can change that. Like in the you can see the in the F split. So in the F split, the only thing you can do the split fraction or flow. So like suppose if I'm using the S split, na, then I can only define either the split fraction. So suppose your mixed stream will contain water, benzene, and toluene. Suppose in ratio like 1:3 ratio 2. Okay, this will be your the composition of mixed stream. Okay, so this will contain all three components. Then you can only define the fraction will supply line 1. So this fraction will also contain all three components, but it will be the fraction of the whole stream. Okay, and similarly you can also define the flow. Like suppose your this flow is like maybe 3000 kg per hour, because 1000 is each, so it will be like 3000. Okay, then you can define like I need 1500 kg per hour in supply line 1, then I need 500 kg per hour flow rate in supply line 2, and remaining in storage. So this splitter will split this mixed stream into these flow rate, but the composition will be same. So this stream will also have 1:3:2. It will also have 1:3:2, and this is also 1:3:2. So there is no change in the composition. You are just splitting the mixed stream. Either you can define by the fraction or define by the flow rate. But if you will use the F split, then you will have more option like limit flow, cumulative flow, like that. Suppose your system is like maybe because when like this is like example, so we have already fixed the flow rate, but when we work in the real condition, then this flow rate can change. Okay, maybe suppose there is shortage of water, so maybe this flow rate will come to the 500 only, and due to that you want to maintain the same ratio, so you will also decrease the flow rate of benzene and toluene. But but you have connected a component in supply line 1 that need a fixed flow rate. Okay, so if that component that is connected to supply line 1 don't have the fixed flow rate, then that component can damage. So with the S split, like with the F split, you can define Like the supply line 1 should always have this kind of flow. So that will prioritize actually. So you can define the cumulative flow like that option. Let me show you with the example. So I have already in this we are using the S splitter. So we have only the split fraction option and the flow option. Only two options are there. Okay. Let me close this. Yeah. So now we are having the same inputs, okay, the same mixer, but now we are having the F splitter, not the S splitter. So see, if you go to this, then you have different options. Like you have three streams: storage, supply 2, supply 1. So you can define the limit flow, okay. So you can have see the options. So in the S split, we only had two options: split fraction and flow. But here you can see we have multiple options. Okay, so you can use these options as per requirement. So now like we are using the supply line to limit flow. So it will limit the flow rate to supply line 1 to 1800 kg per hour. Okay, and supply 1 will be the cumulative limit flow to 2200. So it will be the cumulative. So first 1800 will go into the supply 2, then remaining 2200 minus 1800, like 400 will go to the supply 1. And if still there is something, then that will go to the storage. So these kind of things we can do in the F splitter. So we have more control over the distribution of the mixed stream. Okay, so you can either use the cumulative limit flow, the volume limit flow, the fraction, the cumulative volume limit flow. So you have different options. Okay, you can also like use the mass basis or mole basis, okay, or standard volume basis. So you can also use the basis for that. So like these option we can choose, and you have to define the stream order. So the supply 2 will be the first order. So your splitter will prioritize the supply 2 with the first priority, then it will go to the supply 1 with second priority. We can also define the priority here. Okay, I think the doubt is clear. Okay, any doubt regarding this?
No, sir.
Okay. So now we have separators. So in separators, the flash of the we are having like flash 2 and flash 3. So flash 2, like these two separates feed into two outlets, vapor liquid, while flash 3 separates feed into three outlets, okay, vapor liquid liquid. So it depends on your input. So if you want to separate in vapor liquid, you can use flash 2. If you have want to separate like vapor liquid liquid, then you can use flash 3. So use rigorous VLE or VLLE, okay, methods. Then use for flash or knockout drums, evaporator, single stage separator. These are the use for this flash separator. And we have decanter. So decanter is used only for liquid liquid separation. If you want to only the liquid liquid separation, then the decanter will be used. For vapor separation, if your mixture can have vapors, then you need to use place 2 or place 3. With decanter, you can only separate liquid, and you can use the density, or like one will be the heavier or one will be the lighter. You can that method to separate. Then there is a separator. So the shape in the model palette, you will find this is as the shape. So it separates feed into 2 or more outlets, while shape 2 separate feed into only 2 outlets. So in shape you can connect multiple outlets, but in shape 2 it will separate into only 2 outlets. And one need to specify inlet flow condition wise with temperature, pressure, flow rate, and composition. You need to define these conditions. And like if m number of outlet contains n number of components, you have m number of outlets, n number of components, then total number of unknown is m into n. Then there are n number of equations. This one one mass balance will be there, and n1 minus 1 be component balance. So degree of freedom will be mn minus n or n mn minus 1. For shape 2, the degree of freedom is 2. So it's only separated into 2 outlets. So it is used for distillation, absorption, and for avoid computation time. So we will see the shape models. So this is the example of the flash separator. So here you can see so first you can see a mixture like, okay, so we are mixing the feed, that is 18% mole naphthalene and 26% mole toluene, then 56% mole water. Then you can see the air. Then this is vapor liquid separation. Then you are separating vapor. This is liquid. This is liquid. So you have a problem. You have the inlet conditions. Okay. You know these like outer will be vapor, oil, and liquid. You know the temperature of this flash. Okay, the temperature and the pressure. Now we will see the Aspen model for this. So you can see here. So this is the mixer block that we are using. Then we are using a this B3. So B3 you can see this is place 3. Okay. So you can also change the cosmetic of this separator. Actually, you have multiple options. So you can use either this one, this one. So you can use as per your like requirement like that. Or if you want to like show them, like you want to show them like this one in this shape or in this shape. So the like physical shape, that kind of system you have, so you can use that kind of shapes here. Okay. So here we are using like this shape. Okay. So we are having one stream of feed. So we have a mole percentage of different components, then the air. You can see we have two streams, stream 1 and 2. So let's go to the stream 1. So stream 1, we have defined the air. And first you need to whenever you start this the flow sheet, then you need to define the components. As I already told you, when you start a new simulation, then first define all the components that are going to be used in your simulation. So the components was already defined. I am directly in the simulation environment. Okay. So for air, we have defined the air. We have defined like the mass flow rate because we have given in the mass flow rate. You have more options here. Okay. Then for stream 2, see, it's mass flow rate. Okay. But I think it's mole flow rate. We have given mole flow rate. So we have given mass flow rate, but the fraction is in mole. So it's important thing. So you have mass flow rate, but the composition in mole fraction. So you need to define as per that only. So define here the total flow rate basis will be the mass flow rate. This is the flow rate, but the composition of this stream is in mole fraction. So you need to define the mole fraction. So be remember always be specific about the composition basis and the flow rate basis. Okay, you can change this composition like the mass flow like mass fraction also, but that can change the result. Yeah, Amit want to say something? Yeah, please.
Yeah, sir, please, in a starting, how to
Yeah,
select the method? It's like as the NRTL and something else.
yeah. Regarding it, like if you know, like if you have a problem, like a theoretical problem from a book, then they will specify the method you should use. Okay, or you can use the method assistant. So Aspen has a method assistant. You can use that. So let me show you that example. So when you go to the help, okay, then you can
Okay.
see the use property environment. So this is the complete manual. So you can read this manual, and here you can read more about the methods. So physical property methods, okay. So what is the property method and choosing a property method. So overview. So in this Aspen, it will ask you some basic question. Based on that, you can use your property method. So like recommended
Okay.
property method for different applications. So like what is your application based on that? Like suppose I am working with the oil and gas production. So these are the recommended method, Peng Robinson's like that. So it depend on the like if you are in gas processing, then if you are working with acid gas adsorption with water ammonia, you should use this method. If you have gas dehydration with glycols, you should use this method. Okay. So Aspen has complete database of all methods and also have like complete reasoning for the methods. Okay. So there is also a guideline. So see this type of guideline. So it will ask you some question. So you have to give the questions like answer, then it will automatically take you to the right method.
Okay. The second question is,
Yeah,
after entering the component, uh, estimate using Unifact for binary interaction finding. So
yeah.
what is the Unifact estimation? All methods are only for an NRTL.
No, it depend on actually I'm not from the chemical engineering background. So for more explanation, you should take help of the Aspen or you can take online help. But Unifac is like for if you want to like more interaction like binary interaction, then we select Unifac. So like suppose we can search here. So yeah, we have Unifac like Unifac activity coefficient model. So for some time to know more about the activities about the various component, we need to select the Unifac estimation. Otherwise, you will have like different results. So it depends on your problem. Actually, I'm not expert in this field, like regarding when to select Unifac and all. So you can use this manual and you can find more detail about this. So you can see the estimation input Unifac group sheet. So you can see here all the why we need to select it and all. Okay.
Okay, thank you.
Yeah. Okay. So yeah, we were on this problem. Okay. So yeah. So this is important. Like, be specific about the flow rate basis and the composition basis. So now we have used the mixer. So here we don't need to specify anything. It will automatically take the inputs. Okay. Then there's a mix stream. So here for the flash option we have three options, like temperature, duty, and vapor fraction. So in our particular problem that we are solving, we have given the temperature and pressure. Okay, that's why we are using this temperature and pressure. Suppose if you have something else, like if you have the duty, you can use that. If you have vapor fraction, you can use that. Okay. Similarly, with pressure, duty, and vapor fraction. So we have given these things. Then there is a key component option. So if you want to select like key component second liquid phase, if you have more specification regarding your second liquid phase, then you can select it here. Like your key component in second liquid phase should be this. So you can define that. But now we don't want to define it. So you have more options there. Like if you when you learn the basic things, then you can use these further options to like to for the complexity of your system. So now if we run it, so it's I think it was already. So you can go to the streams. So here you can see the results. Okay. You can see the mass flow and all. So air like 1500 kg per hour, 500 kg per hour, and there is this ratio. Then this is the mixed stream. So they are mixed together. The total flow rate is 1500. Then they are separated. Okay. So you uh, see the water. Okay. So the mass flow rate of water in this stream 5 is only 0.13. Okay. The 5, this one is the 5. So it's only the 0.13. So it will separate components differently. Okay. In the stream 6, you see the water is 147 and the 428.8. So we have only used the inputs that we have given in particular problem. So it will separate like that. So you can use the inputs that you have in your problem, and you can further specify the conditions, and then you will get the desired result. Okay, then we have another example of a decanter. So here we have a feed like 50 weight% xylene, then water, and we have the flow rate, temperature, pressure. Then again there is a decanter. So we have upper and lower. So like here we have already specified apply NRTL property method and estimate using Unifac. So if you have a theoretical question, then they will specify the method that you should use this method or use estimation using Unifac. Okay. If they have not specified, then you have already have the components, you know about the process, so you can use the method assistant for this. Let me close this file.
So
Yes.
So sorry to ask again, but where is the result button? Like where you just click and you get the result?
Okay,
I can't
in,
understand.
in in this in this I will show you. So let's start from the scratch. So let's see. This is the new simulation. Okay. So here we have given the feed. So water and P xylene. Just type it in the components. Water. Okay. Then P xylene. So it is automatically defined. Okay. Suppose if you don't find with the name, then you go to the find and do the exact find component. Okay. Then go to the next. So here you can see the method assistant. I think one of you were asking about the method. Okay, so you can use this method assistant. If you click on it, then it will take you to this page. Again, the manual page. Then you will need to specify the process type or component type. Suppose you know the process, click on it, and what kind of process you are using. Okay, so suppose you are using in the chemical, click on it. Then what kind of chemicals you have, you can select that, and further you can click, you can use this assistant to know more about the method that you have to use. But as we have given already, apply NRTL property method. So just select NRTL. So here is the NRTL, select it. Okay, so it's selected. Then click on the next. Then here it is defined. Okay, so here is the option for estimate using Unifact. So as we have given already, so it will estimate the missing binary parameter. So some binary parameter is missing if you're not selecting the Unifact. Okay, but maybe those binary parameter interaction are very important for this P xylene water, like this decomposition. Okay, so you need to estimate these to get the proper result, so that the each interaction will be estimated. So click on it, click next. Okay, so on the bottom left side you can see there is option, the result available is there. So result available is there, and you can see no red box in the last class, as I told you. So it means that your system is okay. So you can see you have a blue circle with white arrow. It means it's okay. So your property run is okay. You have already, like with this definition, you have defined the properties, you've defined the components, you've defined the method. So the the basic requirement for any flow sheet, that you need some components, you need a method. Okay, you have already defined that, and it is successful. After that, you have to go to the simulation. Now go to the simulation. So now you came to the simulation. Here you can use this model palette. You can use different kind of systems. Okay, so in this case, suppose we want to use a decanter. So click on decanter, click here. Okay, now you can, if you again click it, then it will put one more block. If you again click it, then it put one more block. To avoid this, just do right click. Now this option is deselected. Okay, so if you click now, left click, it will not put one more block. If you want to delete this block, just click it, press delete button. Click, press delete button. Okay, so in our this problem we have one feed stream and one upper stream and one lower stream. So just click on the material, and also here you can see, if we are working with material, then we use these represent the stream actually. So if you are working with material, you use the material stream. If you are working with heat, like if you are using the heat exchanger and all, you can use this heat stream. If you are having like mechanical work, you are using some kind of compressor power, like that kind of system, then you can use the work stream. Okay, so like material stream. So now you see three arrows are there, and all three are red. It means you need to specify all these three, otherwise your model will not run. So click on this, click on this, click on this. Okay, so you have connected all three streams. Then just press the next button, the uppermost, or you can go to the home. Then here is the next, or on the top of also you can see the next button, or you can press the F4 button. So click next. So it will ask, see the S1. So it is asking about the S1. Okay, the material stream. So you see this circle with half red, half white. So it means the input is incomplete. So you have given options like feed is 58% and 58% and 200 kg per hour and 30 and 1. You can define temperature is 30 and 1 bar is the pressure and the mass flow rate. How much? It is
2000.
Yeah, 2000 actually. So it's 2000 kg per hour. Okay. Then you can define now. See, we have given the weight percent. Then you need to define the mass fraction. Okay. Yeah, it's mass fraction. Okay. Then it's 0.5. Then it's 0.5. Okay. Then click next. So now it will ask you about the decanter. So for the decanter, we have given pressure and temperature. So 40 degree and 1 bar. So define 1 bar and temperature 40 degree. Okay. When you define these two, see the option is this blue tick. It means your input is complete. Okay. So do we have any other input? Okay. So we have only my upper and lower. Okay. So just click next. So it will say the all required input is complete. You can run the simulation now. Okay. So you can see all is blue and at the bottom result is available. Now see the left corner. Okay. In the left side, you can see this window, left window. So here you can see this, like the block B1 is a decanter. Here you can see the stream results. You can click on it. So here we can see the stream results. Okay. So these are the results that you were asking. You can see here, or you can also go to the results summary. This section you can also go here. Here you can also see the streams result. You can see the run status. Suppose if you have any error, then you can go to the run status and it will show you the calculation were completed successfully, and it will show you the time and all basic things. Okay. In the status button, it will show you the message. If you have any error, that will show you here. Okay. Or streams, you can see the results here, or directly in this block. Like if you go to this particular block stream result, then it will show you only for that block's result. If you go to this result summary, then it will show you for the complete flow sheet. Suppose as of now we are only have one block in our flow sheet, so both will show you the same result. But if I have multiple blocks, then if I want to check the overall result in one sheet, so then I have to go to result summary. Then it will show me all the stream results. Okay. If I want to see the specific results for a particular block, then I can go to the particular block, like blocks. There is option, you can see the blocks, then block B1, because only we have one block as of now. You can go to the block B1. You can go to the results or stream results. Okay. Here you can see. So if you go to the mass flow, so see. So initially in stream input feed we have water and xylene, both per 1000. Okay. And now in stream 2 we have water, almost like 99% water is there, and only 0.2% xylene. And stream 3 we have all xylene, only 0.45% of water. So we have separated both. So we had a mixed stream in which both water and xylene were there. Now we have based on the density, because if you go to the density, then you will see, yeah. So see the density, okay. So see the density of stream 2 is 0.054, and for stream 3 it's 0.008. So in S2 we have water. So water is heavier than the xylene. Okay. So based on the density, it's separated, and the given condition of the decanter. Okay. So this is the basic working with the Aspen. Like, you can select a property method, you can select the components, you can select the model from the palette, and you can give the inputs, and you can use the inputs that have given, and you can play with the more inputs if you want, and you can see the results. So now we have again a separator. So we have one feed, 60 mole percent benzene, then 40 mole percent water. We have given the 1 atmosphere pressure, we have given the temperature, flow rate, then we have mentioned the RK Aspen. So we have already mentioned here this method we have to use. Okay, this is the pressure, temperature, then we have given 3 streams. Okay, and 0.7 split fraction benzene and no water. We have given the conditions also. Like stream 1 will have 0.7 split fraction. Like this is the, so this so we have a feed, so it's a mixed stream. So the 0.7 of fraction will go into stream 1, and it will not have water. Then it will not have benzene, and it will have 0.3 water and 0.3 fraction benzene. So let's see this example. Okay, it's different one, I think, no? Okay, we will look into later actually. Let's go further. So what is the difference between this separator, F split, and flash? So the separator splits the flow when you know the composition of the outlet stream. Okay. So you need to use a separator when you know the composition of the outlet stream. The F split splits the flow, but you can't change the composition of the outlet stream. So F split will only splits the flow, but you cannot change the composition. In the flash, splits the flow by principle of thermodynamics, but you can't specify the composition of the outlet stream. So in this, we can't specify the composition. In this also, so in the separator, we can specify the composition. Okay, like this. So this is a separator. So we have already specified, like stream 1 should have benzene and no water. it should have no benzene, only water and 0.7 split fraction, and this should have both water and benzene. So in separator, so it will be the same. Okay, because we have one input and three outputs. If you use the SAFE 2, then there will be only two outputs. Okay, so this is a SAFE model. So you can see we have control over the stream. So we can define it should contain no water, it should contain no benzene, like that. So this is the major difference. So separator, you know the composition of outlet stream F split splits the flow only, okay, and can't change the composition of the outlet stream. It will only do the split fraction, mole fraction, like the flow, like that only. The flash, it splits the flow by principle of thermodynamics. You can't specify the composition of the outlet stream. It will use the principle of thermodynamics and separate the compositions. Now heater. So the heater is like one outlet heat stream can be specified for the net heat load from a heater, and there may be multiple input to heater. If only one specification like temperature or pressure is given, heater uses the sum of the inlet heat stream as a duty specification. So it can use the sum of input stream as a heat duty, okay, duty specification. And if two specifications are given, heaters use the heat stream only to calculate the net heat duty. So this is the basic about the heater. You can also find these details in the manual of the Aspen from the help section. If you go to the help, go to the simulation environment and go to the details about the unit models. If you go to the heater, then you will find all the details. So this is a basic example. Here you can see we have two streams. One is benzene and one is water. So water is at 300 degree and the flow at 600 kg per hour at 10 bar is 30 degree and 600 kg per hour and 2 bar. You can see the water is at higher temperature and the benzene is at lower temperature. So if we have a heat exchanger like a heater, then it will take the heat from this water and will give to the benzene. So there will be a heat exchange. Okay, and we have given this condition like 2 bar and 10 kilowatt. So we need to give the heat duty to benzene at 10 kilowatt. So we want to give 10 kilowatt to this benzene stream. So we have specified here. So the duty is 10 kilowatt. Okay. So now basically we need to extract 10 kilowatt heat from this water stream. Go to the Aspen. So here you can see the results. Okay. So we have a water stream and we have benzene stream. So the input. So this is the only benzene. You can define the inputs for this stream as we have given here. You have the flow rate, you have the pressure, you can define these. So directly go to this heater options. If you go to the heater section, then you see the input. So you have options to specify. So the specification. So you can choose like pressure, temperature change, pressure drop correlation parameter. So here we have given the pressure and the duty. So we use the pressure and the duty. So we have specified the pressure will be 2 bar and duty will be 10 kilowatt. You can also change the unit from here. You have multiple options. Okay. Then you don't need to define anything else. You just define this. Okay. For this also, like we have two heaters. One is here and one is here. Here we have both the pressure and heat duty, and here only we have pressure. So just define only the pressure. You define the 10 bar. Okay. So let's run it. Go to the result summary. or you can go to the heater actually. So the results. So you can see the heat duty. So it will be, if you want to see in the kilowatt, it's 10 kilowatt. Okay. And if you go to this heater, it will be minus 10 kilowatt. Okay. So this one is the water heater, and this is the heater that we used in the benzene system. Okay. So the water heater is duty is minus 10 kilowatt. So minus 10 kilowatt is going from this stream. So it is giving, this heater is giving minus 10 kilowatt. So minus is representing the output. Okay. So outlet. So sorry, the heat is it supplying the heat, and the block B1 is taking the heat. Okay. So this is taking the heat. Okay. 10 kilowatt. So this heater is giving 10 kilowatt of heat to this one. Okay. And you can see the temperature difference. It's like input is 30 degree. So due to this 10 kilowatt heat, so the output stream is B1. So this bench out. Okay. So go to the result summary. Go to the streams. The result for this bench in and bench out. So see, the temperature was 30 degree at the input, and the output is 33.34. So that 10 kilowatt heat increased the temperature by 3.34 degrees centigrade. And for the water, the input was 300 degree and output is 269.8. So temperature is decreased. So this decrease in temperature means the heat is it's releasing the heat to this benzene. Okay. Any doubt?
No, sir.
Okay. In this way, you can use this simple heater. Now we also have a heatex. So as you go to the Aspen, in the pellets of the exchanger, so we have heater, we have heatex, we have M heatex and HX flux. So we have multiple options. So we have now seen the heater. Okay. Now in heatex. So what is about the heatex? So heatex can perform both simplified as well as rigorous rating calculation. So the previous calculation was very simple. So in that we didn't we have to not define any like fin sizes, any the geometry of exchanger, nothing. We are only specifying the heat duty or the pressure and that things. Okay, so it's a simple calculation. But in heatex we can do rigorous calculation. So for rigorous calculation, the geometry of exchanger must be known. So heatex can perform the following. So the heatex can perform full zone analysis, heat transfer and pressure drop calculation, sensible heat, nucleate boiling, condensation film coefficient calculation built-in for or user-specified correlation. It's have some built-in correlation and you can also define some correlation. Heatex can model shell and tube exchanger of the following types. So it can model counter current, co-current, segmental baffle like TEMA, EF, GH, J and X cells, road baffle, TEMA, E and F cells, bed and low fin tube. So these are some types of heat exchangers available in the market. So it can do the heatex can perform the calculation based on these type of exchangers, and you can do the rigorous calculation also. We will look into it. So heatex cannot perform mechanical vibration calculation and estimate fouling factor. So these are the limitation of heatex. It cannot do the mechanical vibration analysis and fouling factor. And one of the following specification has to be selected for heatex. Like when you are using the heatex model, so you need to specify either the transfer area or geometry, exchanger duty for hot or cold outlet stream, either temperature change, approach, degree of superheating, cooling, and vapor fraction. You need to select these kind of specification for your heater. And then there is a M heatex. So unlike other unit operation blocks, M heat X. So that was the heat X. Now M heat X. So M heat X is not simulated by a single computational module. Aspen Plus generates heaters and heat streams to represent the multi-stream heat exchanger. So in this, it is actually multi-stream heat exchanger. So we can use the multiple streams, like multiple input and multiple outputs. So M heat X can be used to represent heat transfer between multiple hot and cold streams. So suppose we have multiple streams, so we can use M heat X. It can do detailed, rigorous internal zone analysis, determine the pinch points. Okay, so we can also determine the pinch points. Then M heat X use multiple heater blocks and heat streams to enhance flow sheet conversion. And two stream heat exchanger can also be modeled using M heat X. If you only have two streams, you can also model that by M heat X. If you have multiple stream like 4 stream, 6 stream, so you can also use the M heat X. So this is an example of M heat X. Okay, so you have given a heater. So see this water, you have given temperature 10 degree, 5 atmosphere, flow rate. Then benzene 30 degrees, 7 atmosphere, 100 kilomole. Both are input. Then we have ethanol 100 degree and toluene 120 degree. So from the temperature, first you need to identify which one is the cold stream and which one is the hot stream. Because when you specify the heater, then you need to specify because the heater, if you go to the Aspen, let me show you. So if you go to the exchangers, okay, if you select, like suppose I have already modeled this, but let me select again, new block. Okay, if I click on the material, so you see there are 4 okay options. So if you click on it, it's a cold required. So basically this stream is for only the cold fluid, okay, and this one is the hot fluid. This one is the cold outlet and this one is the hot outlet. So you need to specify very clearly the hot fluid on this section and the cold fluid in this section. Okay, this is the requirement. So you need to specify very clearly the correct stream connection. So here you can see we have water input, benzene input, and then we have ethanol input and toluene input. So just give me a moment. Okay. So this is the example of the heat X. Okay. So here we have like 2 inputs, benzene and water. Then we have benzene out and water out. So it's a different example. It's for the heat X, not M heat X. Okay, we have only two streams. One is the water. Let's see the water specification. It's 300 degrees centigrade. Okay, so this water is hot fluid. This benzene is 30 degrees centigrade. Okay, so actually is the previous example. If you go to the this example, the previous one, so we did this example with the basic heater. Now we are doing the same example with the heaters actually. So we are using the same example, but we are using the heaters. Okay, so this water, benzene out and ben out. So the options that are available in this heaters is, these are important actually. So you can define the, like, what kind of model you require, like cell and tube, kettle reboiler, air cooled. Okay, and you can define the hot fluid should be on the cell side, tube side. Okay, you can define the calculation like rating calculation, design, simulation like that. Then exchanger duty you can define. We have given 10 kilowatt, so we can define 10 kilowatt. Okay, so you can directly use the shortcut one also. If you use the shortcut one, so if you use the cell and tube, then it will do a detailed calculation. You can like specify the geometry also. Suppose if you click on size exchanger, then it will show you some size detail. See, here you can see you can do the all designing part. You can do all like designing part. You can choose the OD, you can choose the pattern like triangular or fin patterns. Okay, you can choose the baffle types. So you can choose multiple things. So you can click on the, you can define all things, then accept design, then you can do the calculation. And you can find the correct size of your heat exchanger. So in the results, if I run this model, let me run it. Yeah. So if you do the complete calculation, this sizing, for more detail, you can also refer to the class video. You see here, so the required area for this 10 kilowatt heat exchanger, 10 kilowatt of heat exchange is 0.145951 square meter. But your exchanger area is 1.049. So you see, you have very, like, the area is very high as compared to the required area. So your design is over designed. Okay, so basically you are wasting the material and all. You require very less area theoretically. You can do the changes in your design. Okay, you can change the tubing length, you can change the number of tubing like that. So do that, then again go to the results, then check which one is the correct design. So you can choose that design and you can refer that design to your vendor. So that vendor can manufacture the heat exchanger as per your design requirement. So basically you can do the optimization of the heat exchanger design. So for here you can see the summary, like water input was 300 and 270, benzene input was 30 and 33.4. So from that also, and you see the heat duty, it is 10 kilowatt. So with this 10 kilowatt, benzene temperature increased from 30 to 33 degree. Okay. So with the heater model, it was very simple or shorter calculation, but this AM heatex, we can do a rigorous calculation. We can do we can design the exchanger. Okay, we can know the actual area, we can know the required area, we can change the design, we can change multiple parameters, and in that way we can specify geometry, we can specify size, we can specify the size and all, We can change the like kettle reboiler, and we can do multiple things. So this is the heat X actually. Okay, any doubt regarding this heater and heat X? Okay. I think now we should move to the questions. Then if time left, then we will do some more problems. Let's move to the questions. So further we have covered the mHeatX. So the example you can try it. Then we have some columns also. Okay, so in this like distillation column, we can have some feed. We can do the distillation. We can use the reflux ratio. We can define this in the model, and we can change the reflux ratio. We can change the recovery and all. We can change some more parameters. Go through these models and try it. Then the red flag is important. So the rigorous simulation block for the absorption, stripping, and extractive distillation, azeotropic distillation, and reactive distillation. So in the columns, like this red flag is a rigorous model. So you have more control over this. So you can do for absorption, stripping, extractive distillation, azeotropic, and reactive. It can handle highly non-ideal components, can have multiple feed and product stream, and can differentially simulate a column with trays, random packing, or structured packing. So basically, you can define different kind of packing in the column, different kinds of like structure with trays and all. So in this, you can do the rigorous calculation in red flag. Then it is for multi-stage vapor liquid calculation. You can do it ordinary distillation, adsorption, reboiled absorption, stripping, reboiled, stripping, extractive and azeotropic distillation. It's suitable for two-phase systems, three-phase systems only in equilibrium mode, narrow and wide boiling system exhibiting strong liquid phase non-ideality. So these are some more details about this red flag. Can model both random and structured packings and a calculation of size and rate columns consisting of trays and packing. So this is the reactive distillation. In this, like if we have some reaction, this reaction is given, then we can use this reactive distillation column. Okay, we have given the acetic acid, ethanol, then we have a reaction, they are reacting, so we can model this. So I will show you this at the end of the class. Let me just go to the basic questions. Okay. So if there are two outlet stream in the mixer block, then the second stream, sorry, the second one is space stream based on density.
Decant stream.
Decant stream. Anyone else? If we have a mixer, okay. So basically we are mixing, and then there is an optional stream that is decant stream. So that can depend on the density also. Okay. The specifications based on which the streams are split through S split are flow and limit flow, split fraction and flow, flow and cumulative flow, split fraction and limit flow. So we have like
B.
S split and F split. So what is in the S split?
Split fraction and flow.
Okay, split fraction flow. We have one answer. Anybody else?
Split fraction and flow.
Split fraction and flow.
Okay. So are you guys also using Aspen now, or just you are like, are you also using Aspen with this PPT?
No, sir.
Okay, okay. So you can
Yes,
also go to the Aspen, you can check the options also. So in the S split, we have only the split fraction and flow. And in F split, we have multiple options. We have also seen our video in today's class that we can specify the cumulative flow, we can specify the limit flow and all. So this is a example. So the option that will appear in the drop-down menu is indicated by the red coloring ring A in figure 1. So here option A, so in this, the composition, what kind of options will be in this option? So like mass fraction, volume fraction, mole fraction, wall flow. Which one is correct?
Mass fraction.
Okay, only one option.
Mass fraction.
Mass fraction. So whenever, like, remember one thing. So as you can see here, is and are. So multiple options may be correct. So go through all options, then give your answer.
Sir, mass fraction, mole fraction, and volumetric flow.
So we have one answer: mass fraction, mole fraction, and volumetric flow. Anybody else? Okay. So it will give you only the mass fraction and mole fraction. Okay, the volumetric flow, this thing will come into this, or we can go to the Aspen and we can see regarding this. Let's open an example. Suppose if we have air, we have water. So see, so we have mass flow, mass fraction, mole fraction, standard volume fraction, not direct volume, STD, mole fraction, mass concentration, mole concentration, standard volume flow, not volume flow, STD, volume flow, standard volume flow. Okay. So we don't have the direct volume flow. It can be here actually. So the volume flow is here. Okay, mass, mole, standard volume, and volume. So the option that will appear in the drop-down menu is indicated by the green colored ring C. So what will be the option in this C? Mass, volume, standard volume, and weight. Which one?
Mass and volume.
Okay, mass
Mass
and
volume, standard volume.
mass, volume, and standard volume. So we have two answers now. Anybody else? If you have option, if you have Aspen, please go there and check this option. Okay, so the correct answer is mass, volume, and standard volume. As we can see, it's mass, mole, standard volume, and volume. So there is no option for weight actually. The option that will appear in the drop-down menu is indicated by the magenta colored. Ring D, this one. So if you're using this one, then what are the options available here?
Option.
Temperature and vapor fraction.
Pressure.
Temperature and vapor fraction.
Temperature and fraction.
Temperature and vapor fraction. So anybody else? So the correct answer is vapor fraction, temperature and vapor fraction, because temperature is already shown here. So you can also select vapor fraction, temperature, vapor fraction like temperature. So these are the combinations. You can type anything. So basically the temperature and vapor fraction are there. The type of separator model used for liquid-liquid separation.
Decanter.
Decanter. Okay, think about it.
Decanter.
And what will be the basis of the separation?
Density.
Okay. So yes, the decanter. So we can separate two liquids with difference of density using decanter. The outlet of model flash 3 are one vapor, one liquid, two vapors, one liquid, one vapor, two liquids, two vapors, two liquids.
One vapor, two liquids.
Yes, because it's flash 3, so one vapor, two liquid. Then the model shape is component separator, true, false.
True.
Okay. And how many output stream we can have in separator? In model SEP, SEP?
Multiple output.
Multiple
Multiple outlet.
Yeah, multiple
Instead.
outlets. Okay. So it's true. The model block HX flux is used to calculate. So we have a model block here, this HX flux. So what is the purpose of this HX flux? HX flux. The overall heat transfer coefficient calculation.
Overall heat transfer coefficient.
Overall heat transfer coefficient.
Okay. So basically from this HX flux, we can calculate the overall heat transfer coefficient. The model block that uses Win Underwood Eland method is which one? Which model use this method? Extract, distillation, distill, red frac, or DSTW?
Red frac.
Which
Option
one?
D.
Option D. Okay. Yeah. So the DSTW use this method. Okay. For more detail, you can refer to the Aspen help also. Why this model use only this method and what is the purpose of this method? You can refer to Aspen help. So DSTW and distill blocks are useful for obtaining column parameters and provide accurate results. True, false?
False.
Why?
Sir, it provides only first approximation results.
Okay. And then how will you get the accurate results?
Simulating the results obtained from these models and performing the simulation on red frac.
Yes, correct. So basically these models can do the initial calculation or preliminary calculation. So from that you can get like basic results. So you can use those results into the red frac or to do rigorous calculation to get the exact design, exact number of stages, packing, all the parameters and all things for that column, you can use that. But for initial calculation, you can use these methods. So it's false. It will not give you the accurate result. It will give you the approx result. For accuracy, you can use a red flag. The type of distillation which is not performed using red flag model: azeotropic, multi-component, extractive, and reactive. Good question. And how many are like, if anybody is from chemical engineering, if you want to or she want to explain like meaning of this azeotropic, extractive, reactive, and multi-component, please explain. Anybody? Okay, if you go back to the red flag model slide, then we can, yeah, this is the red flag. So you can see it's suitable for like ordinary distillation, absorption, reboiled absorption, stripping, extractive and azeotropic distillation, suitable for two-phase, three-phase system in equilibrium mode. Okay, so these are the specifications. It's like it's useful for these kind of conditions. Okay, so maybe now you can answer this. Yeah, anybody? The correct answer is multi-component. So for the multi-component distillation, the red flag it cannot do. It can for the azeotropic, extractive, and reactive. The multi-component distillation is quite complex distillation and very difficult distillation. I think you need some different kind of modeling or a different. We have more options in the Aspen, so you need to use that. In I think in further classes we're going to look into those also. The red flag can do the azeotropic, extractive, and reactive. So the second outlet stream of a mixer unit in Aspen Plus is called
decant stream.
yes. So the main will be the mainstream and the second is optional, that is the decant stream. So as per norm, which of the following free water methods should be used with SRK property method in Aspen Plus? So these things you will only know when you will
NBS.
okay. And why? The correct answer is steam NBS. Any specific reason for this? Okay, so basically if you are using the SRK property method, and if you use the steam NBS, then your this method works very good with steam NBS only. So it's defined in the Aspen manual also, and for detailed reason, maybe you can refer to for the detailing about this property method. But if you want to know about this, you can refer the Aspen manual where it is mentioned that if you are using the SRK property method, you should select steam NBS. A decanter is used only for liquid-liquid separation. Yes, we have already covered this. So with which among the following is not a valid option in place type in in specification of heater unit in Aspen Plus? So which one is not a valid option in place type in place specification? So we can define some things
I
like
think
duty,
A.
degree of sorry.
Degree of
I think
superheating.
option A, degree of superheating.
Okay. Anybody else? So first thing, it's about a heater. Okay. So you cannot define the pressure drop correlation parameter. You can define the duty, you can define the temperature, you can define the degree of superheating. So if we go to the flow sheet, and if we suppose if we select a heater here, then if you go to the specification, so see, you can define the temperature change, duty, vapor fraction, degree of superheating, and degree of subcooling. So you can define these parameters, but there is no option to define the pressure drop. Okay, so pressure drop calculation correction parameter is not available in this heater unit. Heat unit can perform pressure drop calculation. True, false.
True.
True.
Why? Why the heater cannot like perform the pressure drop calculation and we cannot define the pressure drop, but in Heatex we can do the pressure drop calculation. What is the main reason for this?
Pressure directly proportional to the temperature actually. तो अगर temperature deviate हो रहा है तो we can also perform the pressure drop calculation.
But your temperature
I
is
think
also
so.
changing in the normal heater, na? Because that's also giving you the heat exchange and also heat duty you can apply there. So temperature is also changing in the heater, basic heater. But what is the difference in Heatex? So it can do the pressure drop calculation also. Just think about it. You know the answer, I know. So basically in Heatex, we can do the rigorous calculation. Now anybody want to tell the answer why with the rigorous calculation we can do the pressure drop calculation? We discussed about we can change the area. Is it triggering something in your mind? We can change the fin size, we can change the tube length, we can change the design, we can change the geometry. Okay, so false. We cannot do, is still do the rigorous calculation, but still we cannot perform the pressure drop calculation with this. Okay. But what is the difference in Heatex and the heater? So in Heatex, we can do the rigorous calculation. We can define more parameters in that. Okay. So now we have a question. So Anybody wants to try it?
By pen paper or
No, no,
Aspen
but
Plus.
no, Aspen Plus. No, no, we are in the Aspen Plus software class,
Okay,
so use
okay.
Aspen. Yeah, yeah. No pen paper.
So actually, Aspen is not working. I had told you, na, that I
Okay,
did install it. Huh?
okay,
I got
okay.
some issues in installation.
I think last time in last class, one of you was telling that use the system in the username and like that section. I think that will work. Have you tried that?
Yes, I tried, but I don't know. I didn't found Aspen's license manager in the Windows search bar.
Okay,
I don't know what is happening there. I
okay.
informed to NPTEL team, but they didn't respond.
Yeah, then put in a reminder. Yeah, and I think you in last class you all I think also formed a WhatsApp group. Maybe you can
Yeah, yeah.
also ask help in that group
I
because
asked in the group actually.
yeah.
I yeah, but no one here.
Okay, so somebody can try this. Is anybody having Aspen in your computer, like in their computer? Is anybody trying
Yes.
to do this? Let me know if you are trying, or otherwise I can start it.
Yes, sir.
Okay, so take 5 minutes, 7 minutes, just do it, mm, then we will do it. So we have defined here, you can see we have first, whenever like you have a problem like that, so first read it carefully. So we have a stream of water at flow rate. So we have given the flow rate of water, we have given a temperature and a stream of propanol and flow rate. Okay. So heat exchanger operating at atmospheric pressure. We have also given you have to use the NRTL property method and you have to use the heat ex model. Okay. And you have given the hot stream should pass through the shell side of the heat exchanger and the heat exchanger duty and the LMDD correction factor are 30 kilowatt and 0.85 respectively. And you have to use a with a minimum temperature approach of 1 degree. The flow direction is counter current. Perform a shortcut calculation. So go through each point. In each point, you have given some details. Use these details in the HITEX model. So your first step should be, first of all, you need to define the components, water and propanol. Then define the method, NRTL. Okay. Then define the HITEX model. Then just put these data, flow rate, temperature, pressure, and all things. Then you need to see what are the options available in HITEX model. Because in HITEX model, you can also do the rigorous calculation. You can do the shortcut calculation. So based on that, you need to identify as per your this problem and select particular option and then do the calculation. So now we can also start it. The components are water and the propanol
Sir, sir, extended. Actually, I have written all the values, so I
Okay.
can tell you.
Okay, you have written the values. Okay, it's good.
Yeah.
So now you have selected the components. Okay. So water and propanol. Then go click next. Then we have given the NRTL method. So go to the NRTL. Okay. So when you select the NRTL, then it will automatically select some these data and see. And I think the one question was the Steam NB like NBS. So you can see it here. So here we have tables. Okay, Steam TA, Steam NBS. So if they have mentioned you have to use the Steam NBS, you should use that. But here using only the Steam TA. Then click next. So these are the properties. Then click next. Okay. Now you have defined the properties. So now go to the simulation window. Okay. So we have mentioned you have to use the heat X model. Click on this. Click here. Then click right click. And you can also like increase the size of this. Okay. You can drag it from here. Then the materials. So we have input. What is the input? We have an input stream, and this one, see which this should be the cold stream, and this should be the hot stream. Okay. So which one is the cold fluid? Just tell me.
Propanol.
So make it drop in. Okay. So it is the cold fluid. Then type it drop out. Then we have water in. Water.
Yes,
So
water.
water in, and then water out. So you have connected all the four streams that you have given, and try to rename the streams. Otherwise, you will get confused in the stream results. Okay, when you will analyze. So it's only single block. But if you have a multiple, if you have complete like a a complete flow sheet of different components, then it will be very confusing if you don't have name of each stream and all. So make it a habit. Always rename the stream, rename the blocks. Like it's B1 only. So you can type it heat X. Okay. So it will be easier for you at the end to analyze the complete system. Okay. So now go to the home, click next. So we have given what we have given, the temperature and pressure.
Yeah. Is it propanol?
Yeah, it's prop in. Yeah.
Propane. Oh, sorry. 20 is the flow rate and 25 is the temperature. 25 temperature,
25
25
degrees
degrees
temperature
Celsius.
and pressure 1 bar.
And 20. Yeah.
Okay, 1 bar is pressure and flow rate
20 kilomole per hour.
20 kilomole per hour. So you need to select
Hmm.
the flow basis. Okay, 20 kilomole per hour. Okay, then mole flow, and you can select its propanol, right? So 1. Okay. So next, then for water,
Water 50 kmol per hour flow rate and 90 degrees Celsius is the temperature. 90 degree. 90.
90, and the flow
And
rate is
50, 50, 50.
50. Okay. So see, if here we select the 1, so that will be the 1 kilomole per flow rate. So you should select mole fraction, okay, like that. Otherwise, you will get error. So So water is totally 1. Okay, or either you can directly enter the flow rate here. Okay. So
Okay.
for the propane, we need to change it. Actually, in propane, if you see, yeah. So for propane, the input is we entered 1 here, but here it's the mole flow and the unit is kilomole per hour. So it will take, it will confuse or it will give some error. Because here we have given 20 and here we have given 1. It's not in correct form. So make it mole fraction and make it 1. And next, okay, now the heat X. So now here be careful. So you have given, you have to do the shortcut calculation. So you have multiple options here. Shortcut, cell and tube, kettle reboiler. So click on shortcut. Then you have also given the hot fluid is on shell side. So click on this. Then you have given the flow direction. Is it co-current or counter-current? Which one is?
Co-current.
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 Counter-current.
I think one of you is saying is counter-current. Please check.
Yeah, counter-current.
Okay.
So it is given.
Counter current. Last line said counter.
Yeah. So the flow direction is the
Okay.
counter current. So be careful with these data, otherwise you will get some different results. So it's counter current. Okay. Now we have options. Okay. So what we want to do. So if we are doing the shortcut, then basically we are doing the design calculation. So we can specify what we have given. We have given the
Exchanger duty.
exchanger duty. So go to the specification, then find exchanger duty. So we can define this. And what is that exchanger duty? How much?
30 kilowatt.
30.
30.
So 30 kilowatt is exchanger duty. Okay. And what else we have given? The temperature approach?
LMTD correction factor.
Okay. Yeah. So now see. So if you don't enter the LMTD correction factor, okay, but still if you see very carefully, so you don't see any red circle, like red and half white actually. So basically the all inputs are complete. You can do the calculation now. Okay, let's see, try to do it. Yeah, all required input is complete. You can run the simulation now. Click OK. So system is running. We have results. Go to the result summary. So we have results. See, the temperature of input is 25, but the output is 56, and water in is 90, and the output is 62. So we have some heat exchange here. Okay, and if you go to the heat X, then you can see the thermal results. So it's doing 30 kilowatt of heat duty, and with this duty, it's doing this calculation. You can see the geometry results, and you can see the other details also, like exchanger details. So you see the exchanger details. So the duty is this one. The required area is 0.99. Actual area is 0.99. Okay. So UA is LMTD. See, the LMTD corrected is 35.4678. So you can see the geometry results. So we did the normal calculation. So it don't show the geometry result and all. So the point is that we have not mentioned this detail 0.85, but still we are able to run the simulation. So be careful when you do this, try to enter all the detail. So if you don't specify that detail, So it maybe it's assuming something. Okay, so that's why we need to specify that also. So to specify that detail, it will be in the LMTD. So go to the LMTD. It's an optional input. Okay, if you define this input, your result will be more toward your desired results. Okay, otherwise there is some different. Okay, so what is the correction factor point?
0.85.
So yeah, so you define the 0.85. Now see, now in some this is changed. So now click next. Now again run it. So now we will have some slightly different result. Let's see. So it's 25, 56. So it's still near to that, but now your result is as the given problem. Otherwise, maybe the heat exchanger, this correction LMTD correction factor was maybe 0.82. If you calculate from that data, maybe 0.86, something like that. But you have to specify clearly. Okay. So that's the point actually. Always specify everything that you have with you. Maybe your system don't require that input, but if you have that data, you need to specify it. Okay, that is the main point. Now we have defined everything. So if you want like different calculation, if you click on cell and tube, then you can choose the size and all, you can do those things. So let's click on convert. So now see, you can do the sizing and all thing. Okay. So and specify these things. So see, so this kind of exchanger is this. So you can specify, you can change the things. Currently, with the current result, we have these kind of things. So you can see the result and you can change the data and you can pick the design and you can see the different results and all. So these kind of things you can do. So actually it's, you need to do it yourself. Try to find some theoretical problems from some thermodynamic books. Okay, so the best things to learn is software like Aspen and any like software with the this thermodynamic calculation and all. So you can try to use a basic thermodynamic book and take that book and find some good examples in that book and try to model them through the Aspen and verify your results. Okay, from theoretical calculation and from the Aspen calculation. Then you will get to know more about how these things are happening, how the mass balance is happening, how the energy balance are happening. Okay, so you can do that thing, or you can also find some good practice problems on YouTube also, or you can refer some standard books also. So do that, do as much problems as you can do, then only you will be like you will have very good expertise in Aspen. Okay, so
Yes, sir. Sir,
yeah, anything else?
so you told us that you will provide us recorded session videos.
Yeah. So these are my details, and I think if you have any specific question to me, you can email me. Okay, and the regarding the videos, 1 minute. So regarding the video and PPT, I think NPTEL team will share with you. I think they have already shared or not. I don't know. Have they shared?
Yes, sir, they have shared.
So yeah, so they have shared already.
Where they
So
shared,
yeah,
like
yeah.
by through email or somewhere else.
They will
Through email
share a
and on website.
yeah. On the website also you will find a link. In that I think there will be a Google Sheet. In that sheet you can find the YouTube link and a Google Drive link. So in Google Drive link you can access the PPT, and from the YouTube link you can access this recording.
Okay, sir. Thank you.
Okay. So I think we have completed our class.
Thank you,
So
sir.
Yes. So, okay. I think today my Aspen was working. Yeah. So
Yes, sir.
it was not an issue today. Yeah. So okay. Thank you everyone. Thank you for
Thank you.
joining.
Okay, sir. Thank you.
Yeah. Thank
Thank
you.
you, sir.